Hello, my name is Tom Mens. Today I will show you how to implement a state design pattern in Java. To do so, I will start with a state chart that has been modeled with the Yakindo state chart tools, and then in a stepwise fashion I will show you first how we can create a class diagram from this model, and secondly how we can then implement the Java code corresponding to this class diagram. But before doing so, let me explain a bit what is exactly the model, and to do so I will switch to the Yakindo environment, which is the one here. So here we see an example of a state chart that models a chronometer which is composed of two main components. We have the timer state, which basically starts counting from some set value in the variable memTimer and starts decrementing this until we reach 0, and then it starts ringing. And the second component is a stopwatch, which has basically the opposite behavior. We start from 0 and then we start running upwards, so every second we increase the counter by 1. We can switch between both modes, between timer and stopwatch modes, by using one of the three events. So there are three events that are modeled here. We have the left event, the right event, and the up event that allow us to model the entire behavior. We see that we have a composite state chart, so we have two states that contain substates. Some of these states are state charts by themselves, and we also use history states to remember in which state we were before leaving the composite state, so that we can go back to exactly that state in which we are and continue with the behavior that we were actually running. I'm going to show you the Java code that has been implemented based on this. So let me perhaps first start to show you how the timer functionality is working. So as I already explained, we have three events, up, left, and right. The idea is that so in the swing graphical user interface that I have used to implement a very basic rudimentary user interface for the application, we basically see three buttons. Clicking on the left button will correspond to triggering the left event. Clicking on the middle button will correspond to the up event, and clicking on the right button will correspond to the right event. So when we start, initially we are in the initial state timer, and in the initial state we are in idle. So that's where we are now. We see that we are in timer.idle. So now I want to start to run the behavior. So to do so, I first use the right event, as you can see here, to start setting the value of the timer. So I'm going to memorize the value from which we should be starting to count down. So to do this, I will click on the right button, which is this one here. And as you can see here, now the value of memTimer is increasing by 1. So this is basically every time unit here, every 1 second, memTimer is increased by a value 1. So in the Java implementation, it's not actually 1 second, but every 1/10 of a second to make the application run a little bit more smoothly. I can also increase in steps of 5. In the state chart, it was in steps of 10, but it's just a minor difference. Or I can say I'm done, and then I go back to the idle mode. Again, it's by pushing the third button, so the button on the right, so this corresponds to the right event. If I now want to start running the timer, I can do so by clicking on the up, which corresponds to the middle button. So then I start running the timer, and then what will happen is that you see that the timer goes down one value at a time. So that's here, what is here, every 1 time unit, the timer value is decremented, and we continue to do so until either we click on the middle button, which triggers the up event, and then basically the timer simply pauses, and I can again click on the middle button, which corresponds to the up event, to continue decrementing the timer, and we can let it run as such until the condition timer equals 0 is satisfied. And in that case, what will be happening is that we will hear a chime ringing until we stop. So that's what's happening here, and until we reset. So this, which happens by clicking on the right button and we go back to the idle state. Okay, now, so this is the timer functionality. To change the mode from timer to stopwatch, I have to click on the left button, and now I'm in the stopwatch mode. Initially, I have the values of total time and lap time that are needed for the stopwatch are 0. Okay, maybe let's just resize this. Okay, you can start running the stopwatch, which is the middle button, which corresponds to the up event. And then we see that the total time is increasing one by one, which is what's happening here. Every one time unit, total time is increased by 1. I can also split so click on the middle button to have a temporary lap time, which will remain for a couple of milliseconds here, and then we continue counting. Or I can reset and then the time goes back to 0. So that's basically a basic stopwatch functionality. So now we have seen what the state charts for timer plus stopwatch functionality looks like. I will first show you how we can implement, how we can model these behaviors using a state design pattern by means of a class diagram model. So the first thing I've already put here in this modeling environment, which is, by the way, Visual Paradigm, is the basic thing that you have seen already in the Ring application. So there is some graphical user interface which has 3 buttons, B1, B2, and B3, the left button, middle button, and right button. And there is some kind of observer design pattern that is used so that whenever a button is triggered, there will be a message that is sent to invoke the left operation in a class that's called context. When the middle button B2 is triggered, is clicked, there will be an invocation of the up method in the class context, and similar when B3 is clicked, the right method will be invoked in the class context. So how this actually works is that there is a listener implemented using the Swing library, but we will see this later when we dive into the Java details. So we have a class context that basically has 3 actions, left, up, and right. In fact, there is also a 4th action, namely that every time the clock is ticking, there should be something that's happening. Now, how can we implement a state design pattern? To do this, we have, of course, to associate a state to this context. So the context knows the actual current state it's in, so it keeps track of its current state. So I will just do this by means of an association. So the context keeps a pointer to its current state. And the current state basically should reflect all of the different states of our state chart. So we can add these operations. So in every state there should be some entry action as well as some exit action. There should also be some transition that allows to specify how to go from one state to the next. Whenever you go from one state to another, we pass the new state that we want to go to as a parameter, and the result of doing transition will return this new state. There's another thing we can do in a state, so the basic do action. Whenever we are in a state, we can do something, and this something will be implemented by the do it operation. And then also we have to delegate the behavior of responding to the left, up, and right operation to the actual state that is supposed to implement this behavior. So here we are going to repeat these 3 operations: left, right, and up. Maybe one more thing. These left, right, and up actions, as we have seen in the state chart specifications, sometimes they will allow to go from one state to another. So by invoking implicitly the state, the transition operation, they can go to another state. So to facilitate it, we will here have as a return method state. The transition method by itself, it's not an operation that's supposed to be visible to the outside, but it has to be reused in, it may be reused in substates. So let me make this into a protected field rather than a public field, so that only subclasses can access it. So you can see this by this symbol, which is plus for public, and this symbol represents protected. Well, if we go back to our state chart, then we can see that there are that it's a composite states chart that has two main states, timer and stopwatch. So in the state design pattern, it's pretty easy. I have to create two subclasses of state, one that represents the stopwatch and one that represents the timer functionality, and both are subclasses from state to stopwatch, and another generalization from state to timer. So in the specification of this class, I should declare it as being abstract. We can see it's best now because now it's shown in italics. The same for the stopwatch and the timer, as we can see in the state chart specification. So let me go back. Timer actually is also a composite state, so we are never in timer itself, but in one of its substates. So timer also and stopwatch should be abstract states. So I will change it into abstract in their specification. And then actually the real implementation is in substates of these abstract states. So then we go again one level deeper, where we have actually the concrete substates of each. So for stopwatch, if we go back to the state chart specification, we see that we have reset, running, and lap time. That should each be specializations of this abstract superstate. And for timer, I have the same thing. A timer has idle state, set timer, and active, which are again subclasses of timer. And there's one more level, because active timer has three substates: running, past, and ringing. So of course this means that active timer should also be an abstract class. So now we have to also specify the variables that are used in each of these states. So again, we can turn back to the state chart specification. So we saw that for the timer state, we need three variables: mem timer, timer, and ring, which is a boolean to say whether the timer is ringing or not. So what's the most logical place to put them? In the timer abstracts class, of course. So there we are going to add attributes. The first one is an integer to represent the timer value. Another one is an integer to say from which value we should start decreasing. And a third one, okay, a boolean, which represents the fact whether you are ringing or not. Since we are also using a history state, we should also have a variable that represents this history state. And in this case, well, we know that it's a history state of timer, so it always returns a subclass of timer. And we can even specify that initially this should be set to the initial state, the initial substate of timer, which was the idle state. So for a stopwatch, it's the same. In this case, I need two values to remember the total time of the stopwatch, which was specified in the state chart model, and the lap time, which was also specified in the state chart model. And then I also need to specify a history state, which in this case should be of type stopwatch. should initially be set to the reset state, substate of stopwatch. So we will start from here to explain how, using this class diagram, we can actually implement a Java program that corresponds to this class diagram, and that hence also corresponds to the state chart that we have seen here. So obviously what we have to do is to add all these actions to every operation implemented in this class diagram. So it may look like lots of empty classes over here, all of these substates, but actually they are not empty because they all inherit the operations left, right, up, do it, entry, exit, and transition from their abstract superstate, which is here. As a final step of implementing a state design pattern in Java, let us now see how from this class diagram we can go to the actual Java code. From the point of view of the user interface that we can see here, I have made a small modification. So actually, when we want to run a Java program, we have to always create a main class, which is used for running the application by executing the main static method. And what will be happening is that we will run every X number of milliseconds a certain operation, and the main class will be connected to the context class, and it will also be connected to the user interface. Now, to make the application more generic, the user interface does not necessarily have to be a Swing user interface. It could also be simply a command line, a console user interface. So this is why here I have added an extra abstract class for representing the kind of user interface we have. And for Swing, we will have a user interface that uses different types of buttons, J buttons, and different types of labels to attach to these buttons. But the basic idea of any user interface is that you have first have to start initializing it, and then whenever some changes appear, you have to update the user interface. And in addition to this, there will be event listeners that have to be used, for example, to trigger the buttons. Whenever a button is clicked, an event listener will act and send the event to all those elements that are listening to this. In this case, it will be the operations left, up and right from the context class. So I will show this now in the Java code to make all things more concrete. So here we see the first class is the chronometer main class in Java, which has a main method, which basically creates the chronometer and then defines a context that is attached to the chronometer, and also creates the Swing user interface, which gets passed an extra parameter, which is this context. Like this, whenever the Swing button receives a click on a button, it can directly send this action to the chronometer. So this is how the event listener will work. Once we have configured the chronometer, we can run this method where we see that whenever we run, we update the user interface, and then we wait for X milliseconds. We do other update of the user interface, and we execute the operation that is defined in the tick method, which is defined in the context. So let me now switch to the graphical user interface part, which is defined in the Swing GUI class. So there basically the Swing GUI class defines 3 buttons and some text labels. To init the user interface, we simply add the buttons and the labels to the user interface inside a frame. So we just add them to this frame, and we set the frame to visible. To make sure that the context class receives all events whenever a button is clicked, we are adding event listeners. So this is the typical way in which Swing works. So using the Java 8 mechanism, we can do this in a very compact way. To each button, we can add what is called an action listener. And whenever we receive an action performed on the button, in this case, clicking on the button, we will invoke the method left on the observer. And observer is defined here This is basically the parameter that was passed to the swing GUI from within the main class. So in this case, the event listener, if I go back to the main class, that was passed was the variable C, which was the context class. So all received events by clicking on buttons will be sent to the method left in the context class. For button B2, it will be sent to the method up in the context class, and for button B3, every click will be sent to the method right in the context class. That's all there is to it. To update the user interface, we basically have to set the new text values of the 3 text labels, and we have to set also the labels of the buttons themselves every time we update the user interface. So now let's go to the context class to see how this one is implemented. A clock context, it listens to events received from the 3 buttons, and whenever a button is received, we will either invoke the left operation or the up operation or the right operation. Since the context is basically simply a delegation to the state design pattern, it contains a variable which keeps track of the current state in which the clock resides. So remember that clock state was an abstract state. If I go back to my class diagram, this is the clock state in my Java program. So basically it's an abstract superclass that has many different concrete subclasses. When we set the context class for the first time, we initialize it, then we have to set the current state as the initial state as defined in abstract timer. We will also set the history state of the abstract timer, and we also set the history state of the stopwatch. In this case, just to make it clear that we are talking about abstract classes or concrete classes, whenever I have an abstract class, I have added the word abstract in front of it. So I have an abstract timer, an abstract stopwatch, which are both abstract classes. You can also see here that I have used .instance. This is actually use of the singleton design pattern, but I will come back to this later. So invoking the left operation or the up operation or the right operation in the context basically simply delegates this operation to the current state in which we reside. The same whenever we receive a tick, so every x milliseconds, we will also execute the operation do it in the current state. Let's now have a look at the states and how this one is implemented. Let's maybe start with the abstract timer state. First of all, I have to, if I go back to the specification of the abstract timer in my state chart, then I see that the initial state should be set to idle. So that's what's done here. Here we use again a singleton design pattern. We also define 2 attributes, 2 variables, which we set to 0 for keeping track of the time, and the timer initial value that is called memTimer. And here we see again the history state of the abstract timer class. And then we have to specify the different operations that correspond to clicking on each of the events. In this case, for the abstract timer state, there are no events because they are all defined in the substates, except for the left operation. Why? Well, if you go back to the state chart, if I'm in the timer state, I see that there's an outgoing transition called left, which goes to the history state of stopwatch. So in fact, indeed, although timer is an abstract state, it can receive the left operation to go to another state. From timer, there are no other outgoing transitions, so left is the only transition that should be taken care of. Only the left event has to be implemented. So how has it to be implemented? As you have seen in the state chart specification, we should do a transition to the history state of the stopwatch state chart. The same will be done conversely in the abstract stopwatch implementation, because there we have the opposite behavior. When we are in stopwatch and I receive the left event, then I have to go back to the history of the timer. So if I am in the abstract stopwatch, and I receive the left operation, which corresponds to the left event, then I have to do a transition to the history state of abstract timer. Now it becomes more interesting when we go one level deeper. So for example, let's have a look at the specification of the idle state, which is a substate of timer. So there we see that it can respond to a write event or an up event with a different implementation. So if I'm in the idle state, which is a subclass of abstract timer, then indeed there is an up method that has been implemented, which overrides the one that is defined in its superclass. And basically, it specifies that whenever the timer has been set to a non-null value, then I can do a transition to the active timer state, and I can start counting down with a value timer that is initially set to memtimer. And whenever I will be starting counting down in the active timer, I will decrease the value by 1, but this will be implemented in the active timer state. So basically here there's simply the transition up where there is a condition and a value that is set, which basically corresponds exactly to what we saw in the state chart. Whenever we get up, then we set timer to memtimer. In this case, I realized that I didn't specify the condition that memtimer should be a positive value, but in fact, this was something that I've forgotten to specify in the state chart. Like this, it's actually the same thing for all other operations. So we see that there was another event, write, that has to be implemented for the idle state. The implementation of write was very simple. If we receive the write event, we should go from the idle state to the set timer state. How does this work in Java? Well, simply the write operation should simply trigger a transition from idle to set timer. And this is what we see here. If we receive the write event, then we should do a transition to set timer. Like this, all the other states are implemented. For example, in set timer, let's take this one. For set timer, the left event basically sets the timer to 0. That's what we see here. If we receive the left event, we reset the mem timer to 0. Within set timer, every 1 second, we will increase the mem timer value by 1. That's what we will see in the do it state, because the do it state will be executed on every tick. So every time we get a tick of the internal clock, then we will increase the value memtimer by 1. The final one here, when we receive the up event, then memtimer will be replaced by memtimer plus 10. Well, in this case, in the implementation, I've decided to increase by 5 rather than by 10. But you see, when we receive the up event, we replace the value of memtimer by 5. We stay within the same state, so we are not going to do any transition to another. So the only place where we are going to do a transition from one state to another is when we receive the write event. Then we do a transition to the idle state. I can show you many more examples of states here and how they have been implemented, but it's basically a pretty straightforward encoding of the behavior that we have seen in the state chart, in as far as it corresponds to the class diagram that you see here. As a final thing, I promise to come back to this notion of a singleton design pattern that I have used throughout the implementation. To explain this, let me go in a little bit in more detail in how the transition from one state to the next has been implemented. So as I already explained before, a transition simply, when we are in some state, we invoke the transition method, we pass another state as a variable, and we return this. So of course we have to respect the behavior of a state chart. So whenever we do a transition, we first have to always execute the corresponding exit action of the current state. So this can be simply exit or this.exit in Java. Then we can actually do the transition, which means that we will, as a target value, set the next state that we want to be in. on this target state we execute the entry action, and then we return the target state. So basically executing the exit action, doing transition, and executing the entry action. Now the problem here is that we have to pass a state as a parameter, but states in our current implementation are actually classes, while of course the things we have to pass as parameters are objects. So whenever we have to execute the transition method, we have to instantiate the class to obtain the object that corresponds to this class. So let me show this with, for example, the idle state. Whenever we do an event that corresponds to some transition, for example, when I'm in the idle state and I receive the up event, I will do a transition to the active timer state, but active timer is a class. So what do I need to do? I have to instantiate the class to obtain an object, and I have to pass this object to the transition method. Now here is where the singleton design pattern comes in, because actually why do I use the method .instance on the active timer? In fact, it's not a method that is built in into Java. Normally, we would assume here to have some code of the form new active timer, which is basically calling the constructor of the active timer class to create an instance of this class. But we are not doing this because we are using the singleton design pattern. And here you see an example for the idle class, but we have exactly the same code for all other classes that implement states in our implementation. So the idea with the singleton design pattern is to avoid creating multiple objects of the same class, because we know that we have a state chart, so a state chart can only be in one state at the same time, because in our state chart implementation we are not using any concurrent states. And this means that also it's not really useful to create multiple objects that correspond to exactly the same state. At every point in time, there is only one object that corresponds to the current state. And whenever we have to go to a state that we already visited, we can simply take the object that was already created before, rather than having to recreate a new object that is an instance of the same class over and over again. And this is actually what the singleton design pattern is doing. So it basically simply verifies if I already created an instance of this idle class. So initially there is no instance of the idle class, it's set to 0. And then rather than calling the constructor by default, which is here, new idle, I'm calling the instance method to create a new instance of the idle class. But what I do is I always check if I already have an instance. So if I didn't create an instance of this idle class, which I can see by looking at if this value of instance is 0, in that case, the very first time I have to create a new instance of this class, I will simply call the constructor method and I will put this created object into the instance value. Once I have done this, I can simply return this instance because it contains the object that has been instantiated. But the second time that I want to create a new instance of this same class, well, it suffices to simply take the value that is defined in instance because the object was already created. So if a second time I want to create an instance of idle, in that case the instance will not be null any longer. So I simply return the instance that was already stored in the instance value. So like this we avoid creating the same object over and over again, which is good for the memory consumption because we don't have lots of useless objects running around. And it also ensures us that we always have the unique object that represents the state. So here you see this use of the singleton design pattern, but we also see this in every other class, like here, the same use of the singleton design pattern, and here. So it's always reused over and over again.